This sign is known all over the world as the hazard symbol for radioactivity. The radiation emitted from a radioactive source is invisible, but a Geiger-Müller tube attached to a counter can detect its presence. The greater the number of clicks, the higher the level of radiation. Remove the radioactive source and the count falls, but it doesn't drop to zero. Wherever you are, there's always a low level of so-called background radiation. Whether you're out in the street, in the middle of the countryside, even inside your home, a Geiger counter continues to detect low levels of background radiation. That's because all sorts of materials are naturally radioactive. This rock contains the element uranium. Even this wall tile is emitting radiation. And just listen to this old watch. The luminous paint on its hands contains the radioactive element radium. This is the amount of potassium chloride in an average human being. A small percentage is radioactive. Cosmic rays reaching us from outer space also contribute to the general level of background radiation. To understand what radiation is, you have to go back to the basic structure of an atom. All atoms have a nucleus made of neutrons and protons. Surrounding it are electrons. The nucleus of a radioactive atom is unstable. It can break up at any time, emitting radiation as a result. But because we can't see nuclear radiation, it was only discovered just over 100 years ago. A French scientist called Henri Becquerel accidentally found out that the invisible radiation from a rock affected a photographic plate. We can mimic Becquerel's discovery using a piece of film in a light-tight container and placing our radioactive objects on top. Once the photographic film has been developed, you can see the marks the radioactivity has left behind. A cloud chamber also makes the effect of some nuclear radiation visible. The chamber contains air saturated with alcohol vapor. The metal disc in the middle is a radioactive alpha source. As the radiation shoots through the alcohol, it leaves behind a vapor trail. That's because nuclear radiation ionizes air. When the radiation collides with atoms in the air, it dislodges electrons. These air particles become positively charged ions. As the radiation passes through the air in the chamber, it leaves a trail of positive ions behind. The surrounding alcohol molecules condense on these ions to form a trail of tiny droplets. In this way, the path taken by the radiation becomes visible. Although nothing appears to be happening, all these substances are emitting nuclear radiation. It's invisible, but an easy way of detecting it is to use a Geiger-Müller tube attached to a counter. There are 3 different types of nuclear radiation: alpha, beta, and gamma. Each has a different penetrating power. This is a beta source. It emits only beta radiation. The count rate is over 600 per second. Place a piece of paper in its path and the count rate falls only slightly. Some of the beta radiation has stopped, but most travels through. Replace the paper with a denser material and the count rate drops much further. Beta radiation is absorbed by a thin aluminium sheet. All nuclear radiation originates from the nuclei of radioactive atoms. When beta radiation is emitted, a neutron in the nucleus splits into a proton and an electron. The electron shoots out of the nucleus at high speed. Beta radiation is a stream of high-energy electrons. This electric arc is also a stream of electrons. See what happens when a magnet is placed nearby. Because electrons are charged, their path can be deflected by a magnetic field. The same would happen with beta radiation. So how does alpha radiation behave? This is an alpha source. At this distance, the count rate is about 500 per second. Place a thick sheet of paper in its path and all the alpha radiation is absorbed. When a radioactive atom emits alpha radiation, it loses an alpha particle from its nucleus. Each alpha particle is made of 2 protons and 2 neutrons. Alpha radiation consists of positively charged particles. How would you expect it to behave in a magnetic field? Cesium-137 is a source of gamma radiation. At this distance, the count rate is about 50 per second. Place a piece of paper in its way and nothing happens. A thin sheet of aluminium also has no effect. Gamma radiation is very penetrating. Several pieces of lead are needed to absorb this high-energy radiation. Unlike alpha and beta, gamma radiation is an emission of high-energy rays. It isn't made of charged particles, so won't be affected by a magnetic field. Because alpha, beta and gamma radiation have different penetrating properties, they can be used in different ways. The nuclear medicine department of a hospital uses radioactive materials every day. They're used to help doctors understand what's happening inside people's bodies. First, a radioactive material called a tracer is prepared in a specially protected area. It's designed to accumulate in a certain part of the body. This syringe contains a tracer called technetium-99m. It emits gamma radiation and is one of the most commonly used radioactive materials in nuclear medicine. Once the tracer is ready, it's injected into the patient. In just a few minutes, it'll accumulate in the target organ, in this case, the kidneys. The doctors are trying to find out if this patient's kidneys are functioning properly. Gamma radiation is very penetrating. It easily passes out through her body. She's carefully positioned over a machine called a gamma camera. It detects the radiation and pinpoints where it's coming from. A series of images are collected at regular intervals. The first image captured by the camera clearly shows the size and shape of the two kidneys. Now watch what happens over the next 15 minutes. The radioactivity in the kidney on the right has almost disappeared. This kidney has quickly got rid of the tracer, but there's still a high level of radiation being emitted from the kidney on the left. There's probably a blockage. The left kidney is struggling to get rid of the tracer. But if the radioactive material is inside the patient's body, does this make them radioactive forever? To investigate, a syringe containing a fresh sample of technetium is placed into a radiation detector. At 9 o'clock in the morning, the radioactivity of the sample is 112 million counts per second. After 2 hours, it's dropped to 88 million. After 4 hours, it's 67 million. The level of radioactivity emitted from the technetium sample is gradually decreasing. Radioactive atoms decay, emitting radiation to form new atoms. The sample gradually becomes less radioactive. To investigate decay more closely, this is a sample of barium-137M. At time 0, the activity is 40 counts per second. After 2 minutes, it's dropped to 25. 4 minutes and the count rate is 15. After 6 minutes, it's about 7. The time taken for the activity of the sample to fall by half is known as its half-life. Plotting a graph of count rate against time produces a smooth curve. The activity falls to half its original value in just 2.5 minutes. It falls by half again 2.5 minutes later. So the half-life of barium-137M must be 2.5 minutes. Technetium-99M has a half-life of 6 hours. So how much will the activity have dropped 24 hours after the injection?
Thursday on Catalyst, have our rainforests started to do the unthinkable, disturbing new research that rainforests are beginning to drive the cycle of global warming. And overweight kids with signs of heart disease. But could the solution be just a bit of exercise? And a rescue mission to bring home the brush-tailed rock wallaby all the way from New Zealand.
Look at him!
That's coming up on Catalyst, 8 o'clock Thursday night on